for all I in this set, which is a set of transient states, you have set ui to be ui0, which is basically starting from the transient state I, the Markov chain gets absorbed in the state 0. So in other words, this is the ruin probability of the gambler A if the gambler A starts with rupee I. Okay. We defined u0 to be 1 and u of A plus B to be 0. Then we have shown that all of these successive differences of the ui's are equal. So u0 minus u1 is equal to ui minus u2 all the way up to u of A plus B minus 1 minus u of A plus B. Also, if you take the sum of all of these, there are how many of them? There are A plus B many of them. If you take sum of A plus B many successive differences, the sum of course telescopes, and then you get u0 minus u1, which is 1 because u0 is 1, and this should be u of A plus B. Sorry, this is u0 minus u of A plus B. It's not u0 minus u1, and u of A plus B is 0, so this is 1. So all of these are equal, the sum is 1. So therefore, each of them should be 1 over A plus B. There are A plus B many. So each of them is 1 over A plus B. And this should be A plus B, as I said. So therefore, what you get is 1 minus UA would be U0 minus UA. This would be the sum of this ui minus ui plus 1, where I runs from 0 to A minus 1. So you have A many of these successive differences. This will telescope you to give you 1 minus ua, this sum. So of course you have A many of 1 over A plus B, so therefore this is A over A plus B. So that will tell you that ua has to be B over A plus B. 1 minus ua is A over A plus B, so ua has to be B over A plus B. So therefore, we have shown that if A and B start with rupees A and rupees B respectively, then the probability that A is ruined, which is also equal to the probability B wins the game. Whether we were starting from A because the Markov chain starts at say, A starts with rupees A, so that's why we are writing PA. This happens to be equal to B over A plus. And this of course confirms the obvious case that more money A has initially compared to B, the lower is the chance that A will be ruined. Okay? If A is higher compared to B, then of course B over A plus B would be very small, and then of course A won't be ruined with high probability. Not only that, in fact, in this case, the ruin probability is actually proportional to the amount of money B owns in the beginning. So because ruin probability is the winning probability of B, this is equal to actually B's fraction in the initial capital. So if B owns only 10% in the initial capital, so say A starts with rupees 90 and B starts with rupees 10, then of course the probability of A is ruined would be only 10%. Because B has only 10% money in the initial capital. Okay, so in the initial capital, whatever B's fraction is, that is actually equal to the ruin probability. So the ruin probability of A, which is the winning probability of B, is actually therefore proportional to the amount of money B has in the beginning. If A plus B is assumed to be constant. In other words, you can just think of it as a fraction in the initial capital. Now, this is the solution of gambler's ruin problem when the coin is unbiased. So far we have only shown you the unbiased coin case. So, however, the coin can be biased, which will introduce some bias in the game. In that case also, using star star, one can actually solve Campbell-Stoney problem. And that's what I give you as an exercise. I would ask you to try it yourself. But if you get stuck, it's actually solved in this book, Adventures in Stochastic Processes. It's the example 2.1, 2.11.1. But do try it yourself, and if you get stuck, then only have a look at this book. Because if you try it yourself, you learn how to compute these absorption probabilities. And there are more examples in this book regarding absorption probabilities. You may go through them. It is a good idea for you to learn how to compute absorption probabilities. Okay, so then let's prove the theorem on absorption probabilities. And as we have understood, it's enough to show star star. It's enough to show that this holds. Now we'll take care of this using what is called the first step analysis. So what is first step analysis? We'll try to see where the Markov chain is in the first step. Okay, that's what is called first step analysis. So remember that Uij, where I is a transient state and j is a recurrent state. So Uij is the probability that the Markov chain starting at I exits the set T, which is a set of all transient states, because of hitting the state J. So in other words, the Markov chain starting at I first time hits a recurrent state at J. This is the probability. Now, first step analysis, what it does is you introduce that x1 is equal to k and take a sum over all possible values in the state. So in the first step, if you want to achieve this thing, the first step, you'll have to be in one of the states. So just put it in here and take a sum. Okay? So essentially, you're writing this event as union of so many events. This is a disjoint union, so this probability is a sum. Now note that this k can be either in T or k can be in T complement. So this k can either be a transient state or the k itself can be a recurrent state. These are the two possibilities. Okay. So depending on whether the first step is a transient state or a recurrent state, you split the sum into two parts. This is the continuation of this first step analysis. And then this one we'll call A and this term we'll call B. What we'll do, we'll compute A and B separately and then we'll prove star star. Actually, it so happen that B would be equal to this guy, Pij, and A would be equal to this guy, this sum. See, A is already a sum over K belonging to T. So there is some hope that this would become equal to this. And we'll show that this is indeed equal to this. Okay, let's first take care of B. Okay, so note that we have obtained Uij to be A plus B, where A is this sum. That A is basically a sum at the first step is a transient state, and this is the sum where the first step is already a recurrent state. Now here is the point how to compute B. Observe that if K is already a recurrent state, then this event x tau equal to J, x tau is the first time the Markov chain exits the transient states, it hits the recurrent state J. That's what this means. On the other hand, x1 is equal to K means, and K is already a recurrent state. This means x1 is already a recurrent state. Remember, we are starting at I, which is a transient state. Remember, I was a transient state. Here in this equation, I was a transient state. So we are starting at a transient state. And already in the first step, we are reaching a recurrent state. This means the only possibility is that tau has to be 1. Okay? So remember, tau is the first time you hit a recurrent state. So these two together can happen only when tau is equal to 1 and j is equal to k. So that's the only way. Otherwise, these two events will be disjoint, and this is not going to contribute. So therefore, B is a sum, but B is a sum, but the only contribution will come from the case when K is equal to J. Remember, J is in T complement. So in this equation, J is in T complement. So obviously, J is one of the summands here, but that's the only one that will contribute to this sum. All the other ones will be zero because those two events cannot happen together. Okay? So these two are disjoint unless this happens. So therefore, the only contribution will come from K equal to J, and in that case, tau would be 1, and then this would just become x1 equals J, starting Pi of x1 equals J. And of course, that's Pij. So the second term B here is Pij. Once we analyze what's going on. Okay, so therefore what we have shown is that Uij is A plus Pij. So therefore Uij is this sum plus Pij. So now all we have to do, we have to actually compute this sum. Okay. This is what we are going to do next.